This podcast is brought to you by LMU Munich.
Good morning. Thank you for getting up. So in yesterday's lecture, I talked only about holography and not really about any condensed matter physics at all. So the goal of today's lecture is to try to rectify that. I'm going to spend quite a bit of time contextualizing and motivating a set of questions from condensed matter physics, namely about systems with Fermi surfaces that aren't described by Fermi liquid theory. And to give some context for this problem, it's useful to understand a very coarse classification of states of matter, roughly by how much we understand them, or how little we understand them, but also more precisely by the set of degrees of freedom that you have to include to describe the system at its lowest energies. So arbitrarily low energies, what degrees of freedom do you have to include? And so one set of answers to that question is insulators, where there's a strict energy gap. Is systems where there's a strict energy gap, where this direction. And let's think about translation invariant systems, so I can label states by momentum. So this direction is momentum, this is energy, and then so you see that there's a minimum energy above the ground state of the first excited state. And in such a situation, the effective field theory is either nothing, right? There's no excitations below the gap, or maybe there's some kind of topological field theory, which is the kind of thing that's well defined enough that even mathematicians can study it. And I'm going to talk about these things in tomorrow's lecture. The next level of complication is when at the lowest energies there are some points in momentum space, like here's a point in momentum space, where there are gapless degrees of freedom. So such a thing happens at a critical point. So when, for example, in a conformal field theory, or in some situations when there's a bulk gap, but you put the system on a space with boundaries so that there's some gapless edge modes, in which case there can also be this sort of relativistically dispersing kind of excitation. And in this case, the effective field theory of these degrees of freedom is a conformal field theory, like we've been hearing about. And this is the kind of thing that physicists study. And then finally, there's a third case, which is systems with a Fermi surface, where there are excitations on a whole locus, a whole bigger than zero-dimensional locus in momentum space, where there are zero energy excitations. And in this case, unless they're described by free fermions, we don't know what they do. We don't have a good understanding. There's some question marks there that you can't see. And so that's the basic question. So I'm going to begin with some more description of this sort of post-particle physics understanding of metal. And then I'm going to talk about attempts to use holographic duality to learn about this in various levels of vigor and effort. Okay, so these are some references for this lecture. Okay, so a very basic question, a physics question, is what is the effective field theory, or what are the possible effective field theories for a system that has a Fermi surface? So I guess Tadashi already talked about Fermi surfaces, so I don't have to explain too much about them. But okay, let me remind you a little bit. There's a piece of lore that the answer to, which is it's not true. The answer to that question is that it's described by Landau Fermi liquid theory, and let me remind you what that is. So to begin, imagine that we had free fermions. So imagine that the fermions don't interact with each other, in which case you can find the ground state as a Slater determinant of single particle states. You can understand everything just by thinking about one electron at a time and then accounting for the Pauli principle. And so suppose that this is a picture of the energy of a single particle, of a single electron as a function of momentum, kx, ky. And to find the ground state, you just fill single particle levels. That's this honey-colored stuff is meant to be the filled levels. And you fill them until you run out of electrons. And where you run out in energy is the Fermi level, the chemical potential. And where you run out of momentum is the Fermi surface. And the reason that the Fermi surface is an exciting place is because low energy excitations of such a system are just, you either remove an electron, like the last electron that you put in, or add an electron right above the Fermi surface, though that costs very little energy. Okay, and the idea of Landau for extending this to the interacting theory is that there's some region in the space of interactions where this picture is still accurate, where we can adiabatically deform our understanding of the picture without so any kind of dramatic rearrangement. In which case, the low energy excitations of the interacting theory can also be weakly interacting fermionic charged quasiparticles. So they're basically like electrons, the only difference being that they have to carry around their effects on their friends, on the other electrons that are around, because they do see each other. But the point being that so the lifetime of a state of one of these quasiparticles with definite momentum is finite because it can decay into a state with another momentum. So unlike in the free fermion theory where it lives forever. And so they're basically free fermions with some dressing. Okay, and this is the description of metals that we understand. And one consequence of this picture, this Landau picture, the existence of these quasiparticles, a quantitative and measurable consequence, is that there are poles in the single fermion Green's function, in the psi dagger psi correlator, on a surface in momentum space at k, magnitude k equals kf, the Fermi surface, and at zero frequency relative to the chemical potential. And so this Green's function has a form like this. So there's this linearly dispersing mode as I vary k perpendicular across the Fermi surface. The frequency of the mode changes linearly with some lifetime which is small. This imaginary part of the location of the frequency of the pole is some small thing. And this is something that you can measure using angle resolved photo emission. So here's your thing that's described by Landau Fermi liquid theory. You hit it with a photon. Electrons are charged, and so they care about that. And you can, by photoelectric effect, kick out a real electron and see it. That's an eyeball, or I guess it's an eyeball that sees electrons. And measure the frequency and momentum of the electron that you detect, and you know the frequency and momentum of the gamma ray that you sent in, or whatever. Yeah, I guess it's whatever kind of photon it is, a high energy photon. And so the difference is the frequency and momentum of some fermionic excitation in the system. And in a Landau Fermi liquid, and this thing is the intensity that you see is proportional to the imaginary part of this Green's function, because you see you can only kick out an electron if there is a state with these quantum numbers with that frequency and momentum. And in a Landau Fermi liquid, this thing approaches a delta function on the Fermi surface as you approach the Fermi surface. And so the picture looks something like this. There's this linear, this is k, this is frequency. There's a linearly dispersing excitation that becomes very narrow right when it passes through zero. Okay, and so the fact that these Landau quasiparticles are long-lived, their width goes like some high power of their energy, so they last a long time, and they have a non-zero residue, which you should think of as the overlap with the external electron. The fact that you can kick them out in this way, it's finite on the Fermi surface, and these properties are sort of these properties ensure the reliability of this description of a metal for calculating thermodynamics and transport. Okay, and there's a good reason that people thought that this was the only thing in the world. One reason is that it was phenomenologically very successful until the 80s or so. And the second reason is that there's a very convincing renormalization group argument for its inevitability. Namely, if you ask about this Fermi liquid family of fixed points, how they behave under arbitrary perturbations that you can make out of the electron operator, add all possible self-interactions of the fields, almost all of them are irrelevant at the Fermi liquid fixed point. The only thing there's a marginally relevant perturbation which leads to superfluidity at parametrically low temperatures. And so this is a pretty good reason to think that once you get near this point, you kind of stay there. So if there's something else, it's far away. It's not in this picture. Okay, but on the other hand, non-Fermi liquids actually exist. So things that are metals but are not described by this theory exist. One place that they exist is in this part of the high temperature superconductor phase diagram. So this direction is temperature, this direction is doping, and this is the superconducting dome. And at temperatures above the superconducting dome, there's this so-called strange metal phase where this photo emission experiment produces things that look like Fermi surfaces but not like linearly dispersing long-lived quasiparticles. And among other anomalies, so more precisely, it shows that there are gapless moments at a Fermi surface. It's infinite momentum with some width which is much broader than that of a Fermi liquid, and with some residue that vanishes. And so the working definition of a non-Fermi liquid that I'm going to use for the rest of today is a system where there's a sharp Fermi surface in the sense, but no long-lived quasiparticles. So that's why I call it post-particle physics. Now this is not the only possible definition of a non-Fermi liquid. One reason being that actually the most prominent mystery about this strange metal phase is actually in the transport properties, namely this is the electrical resistivity as a function of temperature. There's this linear T resistivity that goes on that sets in way before the Debye temperature and goes on for a long time. And so this is also a mystery. Okay, but lest you think that I'm trying to talk to you about models of high TC, I want to emphasize another possible way to come across a non-Fermi liquid, which is a question that I learned about from Senthal, which is how do you kill a Fermi liquid? And what I mean by this is the following: there are some systems that have both a Fermi liquid phase and a phase which is, for example, an insulator where there's no Fermi surface. So, for example, this kind of spin 1/2 Hubbard model, where there's these C's that create and annihilate electrons on sites of some lattice, n is the number of electrons with a given n up and n down, or number of electrons with a given spin on that site, and on some lattice. And let's suppose they're near half filling, so that there is a state where you can put 1 electron per site. And this thing is a kinetic term that makes the electrons want to hop, and this thing is an interaction term that makes them not want to sit on top of each other. And we can understand at least some extremes of the phase diagram of the system. If we take T much bigger than U, then the electrons just don't care about each other. It's just a Fermi liquid, right? And at this end, all they want to do is hop, and we understand the thing that there's a Fermi surface. Sorry? Oh, sorry. Yeah, I didn't read my own figure. Thank you. Good. Yes, this end is Fermi liquid, like it says. In contrast, if the interactions are much bigger than the hopping, then each electron just picks a site and sits there forever, and it's not worth its while to move around ever. And this thing is a mod insulator. Okay. On the other, so we've just understood the extremes, and all kinds of crazy stuff could happen in the middle. But one possibility is that there's actually a continuous transition between them. I can't convince you that there is one, but there could be one. And let's suppose there is. There's an interesting mystery about that because the volume inside the Fermi surface, like the size of the Fermi surface in K-space, is proportional, according to a theorem of Luttinger, which maybe Sabir will prove for you, is that to the number of electrons. And the number of electrons is not changing when we vary either T or U, or their ratio. And so it can't just shrink away. Right? So an interesting question is, what does the Fermi surface do when you move from this Fermi liquid side in this direction to over here where there's no more Fermi surface? It can't shrink, something else has to happen. And one thing that can happen is you could imagine a situation where the quasiparticle residue continuously goes to 0. So one way to think about this quasiparticle residue is by making this particular integral of this spectral density of the imaginary part of the Green's function against the Fermi distribution, which is the momentum occupation number of the fermions. So as a function of k, this is the number of fermions with a given momentum. In the Fermi liquid, this picture looks like this. There's a jump in this occupation number at the Fermi surface, which is exactly equal to this quasiparticle residue. In the mod insulator state, it looks like this smooth thing, nothing happens at all. And so you can imagine a situation where that quasiparticle residue continuously goes to 0, and at the interesting point, there would be some sort of higher derivative singularity there, some discontinuity and some higher derivative. And so you should think of this Z as like an order parameter for the Fermi liquid phase. So this critical point is another place where there's a Fermi surface, but there aren't long-lived quasiparticles because this residue vanishes, and other things have to happen too. Okay, so what do we understand about non-Fermi liquids from, before string theory? So one thing I should mention is the Luttinger liquids, and in 1+1 dimensions, which we encountered yesterday, are examples of interacting fermion systems, which can be said to not have quasiparticles. But 1+1 dimensions is, in some ways kind of special. And also, this is well understood. So let's put a check mark there and move on to higher dimensions. I guess the most important thing I need to tell you is that there's a big loophole in this renormalization group argument that I told you about. The loophole is that when I said that Fermi liquid theory was that all of the perturbations were irrelevant except for maybe BCS and a few other things, what I meant was all of the perturbations that you can make just out of the electrons, just out of the fermions. Whereas if I include in my low energy theory other degrees of freedom besides just the fermions, I can make other operators. And so in particular, you could imagine that there's some, say, gapless boson mode, for example, whose origin could be some long list of things, which, it's the job of condensed matter theorists to imagine what these things might be, and they're very good at that. And if we couple a Fermi liquid to such a gapless bosonic mode, then this kind of diagram, where this thick line with the arrow is meant to be the fermion, and this wiggly line is meant to be this critical boson. So you see that the fermion state with momentum k can experience a virtual situation where it's giving up some of its momentum to this gapless boson, and that leads to an imaginary part of its self-energy. This kind of thing produces non-analytic behavior in the Green's function, or in the self-energy at the Fermi surface. It can indeed produce a non-Fermi liquid where the self-energy density plot, as in k and omega, which before was just a straight line, can become this kind of crazy thing where the residue vanishes. So there are lots of I'm not doing justice to the huge body of work on this subject, but let me just say that whatever you learn from that, I think we know for sure that models constructed this way are not, well, okay, maybe Sabir's going to yell at me now, but models constructed this way are not strange enough, in the sense that although we've killed the quasiparticles, it's hard to understand, let me just say it's hard to understand how they can be strange metals in terms of transport, because the fact that the Fermi liquid is killed by these gapless bosons, whose dispersion relation around, is their gapless modes at q equals 0, which disperse linearly, and those are the processes by which you're killing the quasiparticles. And it does a good job of that. It doesn't, however, do a good job of changing the current carried by this fermion. So if I ask about, as you'll hear in great detail from Sean, the problem of understanding the resistivity is understanding how it is that the current relaxes. And in this process, the current is relaxing by this charge carrier giving up a tiny amount of its momentum to this gapless boson. But the fact that the boson has its density of states dominated at q equals 0 means that small angle scattering, it only changes its direction by a little bit, dominates. And so that the lifetime that you use in the Drude formula is different than the single particle lifetime.
My only caveat is that does not apply to the STW.
Yeah, okay. Okay, good. Good.
Where there is large momentum scattering.
Good, yeah, that's right. But only at certain points on the Fermi surface. Okay, good. So this was all in the way of culture, if you like, of trying to motivate this I think still difficult question in condensed matter physics. And so it's worth asking whether we can formulate a tractable description of such a state whose low energy physics involves a Fermi surface, and maybe is described by a Fermi surface, but without long-lived quasiparticles. So a holographic non-Fermi liquid.
In your definition, this Fermi surface is a Fermi surface of an electron, not of any fractionalized.
Exactly. Yeah, so I'm about to emphasize that. Yeah. So I'm biasing the question here. Notice, as Sabir is pointing out, I'm defining the problem in terms of the single particle response of some effectively gauge invariant fermionic operator, right? Something like an electron. That's the problem that I'm talking about. And I want to emphasize that there are other ways of framing the question. For example, you could forget about the single particle physics and just ask about two particle physics. Just ask about the current and the transport. That's basically the perspective that Sean has been taking on these questions, which I guess it's fair to say has been more remunerative than this one. So I'm going to define the problem in terms of, I suppose that I have a gauge invariant fermionic operator, and I can compute its Green's function, and I want to ask, and I'm defining the Fermi surface to be the locus in momentum space where the inverse Green's function vanishes. So it's like a pole, but it's a little bit different, because if you look at a function like this, where there's some crazy dependence on frequency in the denominator here, it's not exactly a pole in frequency, but if you take the inverse of this and set omega to 0, then you can identify where the Fermi surface is. Okay, so that's the problem, and I think an example of this would be worthwhile, even if the toy model that you use to construct it looks very different microscopically than any good model of a real material, even if it's a large N gauge theory or something like this. Because the question is about the low energy physics. Right? We don't understand a framework for thinking about the low energy physics. And the reason that holography might be a good starting point for thinking about this is that even in holography, even the 0th order approximation has nothing to do with any kind of weakly coupled particles in the regime where the gravity solution is relevant. Okay, so now I'm going to talk about holography. So that was the motivation. Are there any questions about the motivation? Okay, do you think it's a bad idea? We'll see. So let's try to study finite density states in holography. What I mean by that is, I want to study a holographic description of a bunch of stuff at low temperature. So this is very different from studying the vacuum of a CFT at low temperature, right? We need to put some stuff in there. And so I want to suppose that our CFT has a conserved U1 symmetry, which is going to be a proxy for the fermion number. And according to the dictionary that we talked about yesterday, that means that there's a massless gauge field in the bulk. And so a natural starting point, it would be perhaps a little perverse to write down any other action, is to add to our gravity action a Maxwell term for this gauge field. So this is, it's just the Maxwell action written in a covariant way. The only evidence of the covariance is the fact that there's the square root of G there. And the Maxwell equation is obtained by varying this with respect to A. It's just the usual Maxwell equation in curved space. And if in the same way we analyze the scalar wave equation near the boundary, if we analyze this equation near the boundary, we learn that the solutions are a constant in Z and a bit in Z that falls off like some power, Z to the D minus 2. And in particular, if we ask about configurations that are constant in space, in the boundary space directions, then the time component of the gauge field looks like constant, which we interpret as the source, and I'm going to call the chemical potential, and a subleading term, so Z is going to 0, this is smaller, and which we interpret as the response. And to convince you that rho is a good name for this, we use this prescription that I described. We compute the canonical momentum of this field. We're thinking of Z as time. The description in terms of the Hamilton-Jacobi is a convenience. It's not really time. And if you compute this, you find this is equal to the electric field. And that turns out to be exactly this quantity here. So that is to say, the source is the chemical potential, the response is the density. Right? That comes from physics. The ingredient from holography is that the density is equal to the boundary value of the electric field. Okay, the conclusion, which maybe you can't entirely see, is that to compute the partition function in the grand canonical ensemble with a chemical potential for this U1 symmetry, mu, and n is the charge associated with that U1 symmetry, the thing we should do is compute the solution of the bulk equations of motion with boundary conditions so that A sub t goes to mu. Right? That determines the chemical potential. Yes, please.
I'd like to ask that ET is not the gauge invariant quantity in the box. If we have a gauge transformation in the box, what's the corresponding?
So good. So there's an important question of which gauge transformations are really redundancies of the description. So gauge transformations which don't approach the identity at the boundary aren't actually change the state of the theory. And so a gauge transformation that would get rid of this constant is not a equivalence. So although it's formally a gauge transformation, it doesn't fall off fast enough to actually relate states that are the same. Yeah. Good. This business about gauge transformations at the boundary is going to be very important for tomorrow's lecture also. Okay, so the ingredients to address the kind of question that I motivated in holography are the following. So we're going to study a relativistic CFT because that's the simple case that we understand with the gravity dual. That's an important assumption. And so there's some metric in the bulk because every CFT has a stress tensor. With a conserved U1 symmetry, like I said, you think of this like the fermion number. We're going to turn on a chemical potential for it to add stuff. So there's a gauge field, a massless gauge field in the bulk, a Maxwell field. And then we should also add a charged fermion. So this is this assumption that there's some operator in the theory which is like an electron. Right? I'm assuming that we could do something like a photoemission experiment. And so that means that there's a spinor field in the bulk. And I'm going to focus on the case where there are 2+1 boundary dimensions, because that's where many of the non-Fermi liquids are. Okay, so the problem that we really want to solve is this one, where the bulk action is this Einstein-Hilbert term with a cosmological constant, a Maxwell term, and a Dirac fermion. And I guess I should also say there's, really it's anto de Sitter, so that's anto de Sitter there, and that's a boundary condition. And we also need to add a chemical potential. I don't have a picture for, I don't know who discovered the chemical potential. And it says something over here. It explains what limit of the parameters we have to take for our classical gravity, for large n, for classical gravity to be reliable. Basically, yeah, probably. I should have put Gibbs there. Yeah, that's right. Good. Okay, so this problem has been studied. There's been like a worldwide attack on this problem in the last 4 years or so, in various quite drastic approximations. And I'm gonna talk about, we're gonna sort of approach the correct solution of this problem in stages. And the first thing to do, which was the first thing we did, is to completely ignore the bulk matter fields. So you see they're kind of grayed out and ghostly, you can't see them, in constructing the saddle point solution, and just study the fermions as a probe. And this is a correct thing to do in a limit where the Newton constant goes to 0, and this basically the electromagnetic coupling goes to 0, fixing their ratio. So in that limit, these things become much more important than that thing. And in this limit, the solution of Einstein's equations was found long ago, I guess by Romans. And the solution with the right boundary conditions, so that the gauge field goes to a constant, which is the chemical potential, is at 0 temperature, is the extremely charged black hole, the Riser-Norton black hole in anto de Sitter space, where the line element has this form. It looks basically like anto de Sitter space. I'm using R instead of Z, sorry. And the emblackening factor has this particular form, which involves not just a mass or a temperature, but also some charge. There's some other fall-off, and the gauge field has this very simple harmonic behavior. So extremal, the word extremal here means t equals 0, and that means some particular relation between Q and M, so that this emblackening factor has a double 0 near the horizon. Unlike the Schwarzschild black hole that we talked about last time, where there was a linear 0 near the horizon, and that's what led us to this business about periodicity in Euclidean time, that the geometry sort of smoothly ended there. Here there's a double 0, for which the physics is very different, and we're going to talk about that. Okay, so yes, we're going to talk about that right now. So the near horizon geometry of this black hole, it looks something like this. This is this picture of ADS I was describing, but it ends at this extremal charged horizon there, the charges. The geometry near the horizon, where r equals RH, looks like this in a convenient coordinate u. So can anybody tell me what spacetime this is? I guess it says it there. So this is the spacetime that we've been talking about. Just it only differs from this other ADS that I was talking about in that there's no analog of the field theory space dimensions. Right? There's only a time dimension and a radial coordinate. But it's ADS2 in Poincare coordinates. And then there's the spatial directions, the metrical along spatial directions just kind of goes along for the ride. And okay, so this geometry has a conformal invariance. Right? Remember, I made this big deal about how ADS has a conformal symmetry, but the conformal symmetry is completely different from the conformal symmetry of the CFT that we started with in the UV. The chemical potential completely breaks that symmetry. And so the picture, and not only that, but the way that the symmetry acts on the field, on the coordinates is very different. Because the symmetry only acts on t, it rescales t, but it rescales x not at all. So a useful way to parameterize that is in terms of the dynamical exponent z. If I rescale space by lambda to the 1 over zx, and then I take z to infinity, then x doesn't scale. So that's just another way to say that x doesn't scale. So this is called z equals infinity scaling. And a picture of the geometry is like this. Excuse me. Here's the UV boundary where the thing describes at energies much larger than the chemical potential, the physics reverts to that of the three-dimensional relativistic CFT. As we go to lower energies, so this is this RG direction, as we go to lower energies, we notice that there's this chemical potential, and then the chemical potential causes this crazy rearrangement of the ground state, which we only know about because of holography, which is described by the near horizon region of this black hole. It looks like ADS2 times R2. It's some kind of infrared non-relativistic CFT with this crazy z equals infinity scaling. Okay. And as a consequence of ADS CFT, we infer that the region near the horizon is described by some dual kind of many copies of a conformal quantum mechanics system, parameterized by points in space. Okay, there's a lot more to say about this. So now let's ask about finding a Fermi surface. To do that, we look for sharp features in the fermion-Green's function at finite momentum at small frequency. And the fermion-Green's function is computed in just the same kind of way that we computed the scalar Green's function yesterday. So instead of solving the scalar wave equation, we solve the Dirac equation. And instead of doing it in anti-de Sitter space, we do it in this charged black hole geometry. And the answer looks something like this. So this is one of these photo emission pictures, except it came out of Mathematica rather than a detector. So this direction is frequency, this direction is momentum, and this is some peak that disperses through 0 in some weird way. It becomes much sharper, and then it takes a little bit of a turn. So it looks very different from the linearly dispersing Landau quasiparticle mode. Okay, and so near this point, it's possible to understand the analytic behavior of this Green's function. It looks like this. So there's this k-perp which measures how far you are from the Fermi surface in momentum. And then there's this curly g, which is a correlation function in that ADS2 theory that I was mentioning. So to understand the structure, let's break it up into the physics at different scales. The location of the Fermi surface, so the value of kf, this k-perp is k minus kf, is determined by the short distance physics. It's determined by all the details of this, what's going on in this box. We're basically solving looking for zero energy solutions of the wave equation in this box. And so that's like band structure, right? The details of where the atoms are in the solid determines where the Fermi surface is in momentum space. But the behavior near the Fermi surface, the low frequency scaling behavior, is encoded in this curly g, and that's determined by this infrared CFT stuff. It's determined by the behavior of the solutions of the wave equation in this ADS2 region. Okay. In hindsight, we can understand the form of this answer in the following framework by thinking about taking a Fermi liquid, so just free fermions, Fermi surface, and coupling them to this Ziegel's infinity infrared CFT, coupling them via a fermion bilinear coupling. So the free fermion couples to some fermionic operator in the infrared CFT, and then basically by summing a geometric series, you can reproduce this kind of expression. So this is called a semi-holographic interpretation, in that you're using holography only for part of this thing. You're using holography only to describe the infrared CFT. And so it's an accurate description of the physics near the Fermi surface. Okay. Maybe I skipped this. This slide has some details about how to understand the behavior of the self-energy near the Fermi surface in terms of the geometry. And basically, it's a tunneling calculation. So solving the Dirac equation in the bulk can be translated into a simple one-dimensional quantum mechanics problem. And but one thing I should emphasize is that there's this exponent nu that appears in the answer. So that curly g that I was writing down behaves like omega to the 2 nu, where nu is a number that's determined by the parameters of the gravity theory, by the charge and the mass of the fermion field. And as we vary those parameters, different things happen. In some regime, if nu is bigger than a half, there is actually a stable quasiparticle, and this thing looks like this Landau answer. If nu is less than a half, then it looks like this crazy non-Fermi liquid thing. And in between, there's the special value where you can't really see the difference, but quantitatively, the physics is quite different. There's a logarithm in the self-energy, and it is called a marginal Fermi liquid in the sense that there's nearly a stable quasiparticle. And this kind of function was written down. The function that came out of this gravity calculation was actually written down in 1989 as a model of this thing, which is, I don't know, I was really excited about that when we found that. Okay, I guess I mentioned that the behavior of the photo emission is not the thing that people might care about the most in the cuprates, but rather this charge transport. And so I guess, so we started calculating the contribution of the conductivity from the Fermi surface to the contribution to the conductivity from the Fermi surface when we first found this thing in 2009, and we just last month published the paper about it, so I guess I have to tell you what the answer was. And the answer is that it's what you'd expect by dimensional analysis. That in the case where the exponent is nu, the resistivity from the Fermi surface goes like t to the 2 nu. And so if you set, but the reason that the answer is the simple scaling answer is interesting. It's that unlike in this fermion coupled to gauge field problem, the dissipation of the current is controlled instead by the decay of the fermions into these ADS2 degrees of freedom. And whereas the dispersion of a relativistic boson looks like this, right? So there's, there's only at q equals 0 are there gapless modes of the boson. This ADS2 thing has z equals infinity. If I replace, omega equals k with omega equals k to the z, which is equals, that's the scale, the dispersion that scales with dynamical exponent z, then this picture looks like this. It becomes very flat at omega equals 0. There are many values of momentum. There are many values of momentum at which there are low frequency modes, off of which the fermions can scatter. And so because of that, the single particle lifetime really does control the transport. And if you set n equals 1/2, you get this linear T resistivity. Now, before you get too excited about that, I need to emphasize that this answer here, the contribution from the Fermi surface, is not the answer you would get if you had this rising inertial black hole in your laboratory and hooked up leads to it. Because there's a whole bunch of other stuff, a whole bunch of other charge density with a larger density that contributes to this sigma dc. And actually, it's translation invariant, so the answer is infinite. So there are a few drawbacks of this construction I've described. The first of which is this one that I just mentioned, that the Fermi surface, this very interesting Fermi surface that we found, is only a small part of this big system. So it's true that this is a non-Fermi liquid from holography in the sense that part of the system is this interesting Fermi surface, but unfortunately there's lots of other stuff there. And that other stuff is actually playing an important role in making it so. A second problem is you might complain that this answer is too universal. Right? So I said that the finite density state, if I ignore the matter in the bulk, is the rising inertial black hole. End of story. Right? And so that says that if that were the the right ground state, it would say that any system with a holographic description, if you put it at finite density, at low energies looks like this. Right? And that would pretty convincingly show us that there's no real system that's described by a holographic system because we've never seen this. Right? So there must be some ways in which all the possible ground states of real matter can or at least some of them can arise. And the third drawback is that this charged black hole violates the third law of thermodynamics, in the sense that it has a zero temperature, non-zero entropy. Entropy is non-zero at zero temperature, which means that there's a ground state degeneracy. So maybe some people still argue about it. It means that it's describing a family of ground states. In the same way, like we discussed yesterday, that the Schwarzschild black hole describes an ensemble, describes a family of pure states over which it's averaging. So in that sense, the fact that this black hole is hiding the true ground state is a manifestation of the black hole information problem. Okay, so these problems 2 and 3 actually solve each other, because the existence of this degeneracy means that this state is unstable. It means, in fact, that there's actually an extensive ground state degeneracy. It means that there are many instabilities. And so you should think of this black hole as an intermediate temperature phase. It's something that you could pass by on your way to the true ground state, starting from high energies. And there are many possible infrared endpoints, which people are vigorously studying at the moment, maybe new ones that we haven't thought of. And which one is the most important one depends on the operator content of the CFT. The operator content of the CFT is encoded in the bulk in the list of fields and their masses in the bulk, right? And so what the fields and the masses and what the bulk action is what determines what the true endpoint is. And so there isn't a universal answer, but one important instability that's sort of often there is that in many examples, especially in cases where we know the short distance description in terms of some string theory thing, there are charged scalar fields in the bulk. And at low temperatures, those charged scalar fields can condense, spontaneously breaking the U1 symmetry for which we turn on a chemical potential and changing the ground state. Such a thing as a holographic superconductor. You can see, by the way, that scalars have this instability, but spinor fields do not. It's quite a remarkable thing that the wave equation knows about this. But of course it has to, because fermions can't just condense. And the origin of this instability has a nice pictorial understanding. So it comes from the fact that black holes emit also charged. Their Hawking radiation involves also charged particles, and sometimes one sign of the charge will, one sign of the charge is repelled from the horizon, the one with the same charge, and the other sign is attracted. And so you can pair produce charges in the bulk. In flat space, they can escape, but in ADS, they're in a box. And so the thing behaves like a gain medium. So it's really like a black hole laser. Okay, and so I think it's worth emphasizing that the existence of this holographic superconductor instability, because I was motivating this question by talking about this region of the phase diagram of high temperature superconductors, and it's hard not to notice that there's, if you cool it down, there's this, it becomes a superconductor, right? So it's not, it's not totally crazy. Something that is kind of, I don't want to say crazy, but very interesting, is that if the spectrum of scalar fields in the bulk involves only fields whose mass is kind of big compared to their charge, then actually they don't condense. There is no such instability, even if you crank up the chemical potential as much as you want. And so this criterion was found by Denif and Sean. And this is sort of in contrast to the situation at weak coupling, where if I have a weakly coupled boson at finite chemical potential, if it's weakly coupled, of course, it's just going to both condense. All right. So that was the first, step in our approximation to understanding this problem that we motivated. This minimal holographic model of this problem. And okay, so the idea for solving this problem one, that the fermions are a small part of the system, a simple idea is to make the bulk fermions more important, right? We ignored their back reaction, and that's why they're a small part. Yes?
Could you comment how did you do that counting that in the first limit the fermions are only just the ordo and the...
You mean what limit did I take?
In the first limit, the fermions only just a small part.
Oh, I see. Yeah, let me draw a diagram which will explain it. So the expectation value of the fermion density, let's say. So the total density is something like rho fermion plus some classical, something that you compute just by, actually this is equal to the electric field at the boundary, the radial component of the electric field as z goes to 0. So this is this thing I was explaining, the response of the system to the chemical potential. But there's another contribution, which is from the fermions, and this is computed via a diagram like this. So actually, it's a Witten diagram, which I didn't explain yesterday, but roughly it's a generalization of that calculation we did of this scalar field scattering, where I send in a current. So this is inserting the current. So this is the operator that I'm measuring, and in order to get a non-zero answer, I have to there's a loop of the fermion, and so the fact that there's a loop means that it comes with an extra factor of G Newton, basically, or it comes with an extra factor of the thing in front of the action, which I'm assuming that they're all proportional to n squared. Inverse, right? And so it's suppressed by powers of n. I'm being very schematic, but the important point is that there's a loop. Okay, so let's try to improve upon that, basically by putting some other factors in there which cancel the smallness of that loop factor. And if we do that, if we make the bulk fermions more important, they'll back react on the geometry. And so that we'd have to include them in this list of things that can change the infrared, things that can change the infrared behavior. Right? And in addition to these sorts of instabilities, the fermions can also change the story. So it may be that there's a stable geometry, a stable infrared geometry sourced by the fermions. So this is sort of a perhaps misguided hope behind the following work. And the problem with this is that it's kind of hard. And so the second limit where we can approach this question is to study heavy fermions in the bulk. So I don't mean heavy fermions in the sense of f orbitals, but in the sense of just make their mass big. Okay, and so an approximation which makes this tractable, which was taken by Sean and a set of collaborators, is this Thomas-Fermi approximation, which is the approximation that people use to study, say, neutron stars in astrophysics. And one way to justify that approximation is to choose the charge and the mass of these fermions, which are to be big, to reach a regime where you can treat the bulk fermions as a fluid, just as a perfect fluid with an equation state which happens to be that of fermions. And so finding a compact object made from such a density of such things, it's natural to call it an electron star because it's a star because it's a compact object which gravitates, but which is not, it's not a black hole, right? And there's no horizon, or there's not necessarily a horizon, and electron star in the sense that it carries charge. So that's something that doesn't happen in astrophysics because of screening, right? Because there's charges of the other sign, which will just glom on there and cancel it out. But here, there's nothing else. Okay, and so, but I have to mention, in the regime of parameters that these guys studied, which is this large mass, the Green's function, the fermion-Green's function, about which I've expressed a lot of interest, is kind of weird. It exhibits not just one Fermi surface, but many, many, many Fermi surfaces. And that's related to this, roughly that factor, the number of Fermi surfaces cancels this 1 over n squared. Is why, why that makes sense. And secondly, the fact that you've taken a large mass of these fermions means that there's lots of back reaction. So they're really doing a whole lot to the geometry. And in fact, they do so much that they totally destroy this interesting infrared CFT. So they just leave behind no trace of the z equals infinity region. Yes, please.
What do you mean by many Fermi surfaces?
So I mean like concentric values of k where they're those poles of the Green's function. So all omega equals 0. Yeah. Yeah, so it's as if you had many species of fermions, like with a chemical potential for each of them, but maybe with different masses, right? So that you have different values of the Fermi momentum for each of them, but many, many, many of them. So it's very weird. It's very weird. And the fact that it kills the infrared CFT means that there's nothing for these fermions to decay into, and so they're stable quasiparticles. So it's a Fermi liquid, but it's a weird Fermi liquid in that there are many species of fermions. Okay, so I need to make...
But the far IR is Canadian 4, right?
I think sometimes it's Lifshitz.
Okay, but there's still a CFT. It's not Z equals infinity.
Right, it's finite-z. Yeah, it's some order 1z.
So there is
Exactly.
no CFT.
Oh, I see. Okay, yeah, you're right. I meant it kills the infrared CFT that we had before.
Right.
Yeah, that particular one. Yeah, you're right. There is still a CFT, but it's not interesting enough to kill the quasiparticles. Let's say. Yeah. Of course, the z equals infinity one is too interesting. Okay, so I need to make a comment about this Thomas-Fermi approximation, which I really wish I had known earlier. So the motivation for this large mass limit was to guarantee that the Thomas-Fermi approximation would be valid. The actual regime of validity of the Thomas-Fermi approximation is actually quite a bit bigger than that. I think it's possible to improve upon this story about electron stars without going to the drastic measures that I'm going to do, but we haven't done this yet. But so to do better than the Thomas-Fermi approximation, it does break down sometimes, as I'll show you. We need to take into account the wave functions of the bulk fermions. So the Thomas-Fermi approximation is an assumption that you can treat the fermions as a fluid, right? It means that you're treating the wave functions of the particles there as point-like, right? That the constant wavelength of each of the states that is involved is very small. The way that the limit breaks down is if you have to take account of the spatial extent of the wave functions of the particles filling the Fermi sea. So such a thing, let's call a quantum electron star, because you see the wave functions of the states. They're kind of smeared out. And so this is some evidence that the Thomas-Fermi approximation can be wrong. This is a picture of anti de Sitter space. This direction is the radial coordinate, and the vertical direction is the density of fermions computed with a constant chemical potential, so a constant electrostatic potential in this background. The dotted line is what you get in the Thomas-Fermi approximation with a mass m. So the density turns on at a value of the radial coordinate when the mass is m, and keeps going. This side is the UV. This end is the infrared. So the dotted line is the same for each of them. And the solid line is the answer you get by filling the correct eigenfunctions of the spinor field. And notice that they're different. They're different. So this is for small mass, and as you increase the mass, they start to agree. At large mass, they're the same. At m equals 8, they're the same. The place where they differ is in the UV. Okay. And so a third limit that we're going to take in our approach, inexorable approach to this question, is we're going to try to find the back reaction of the fermions on the gauge field, but ignore their gravitational back reaction. So this is of both the fermions and the gauge fields. And so a pictorial description of what I'm going to do now is this. So both the fermion and the gauge field are grayed out. Gravity doesn't care about them, but they care about each other. And this is valid if you just take G Newton to 0, basically. That's the limit where this is a good idea. And yeah, okay. And the quantum field theory interpretation of when, so remember G Newton is a parameter of the field theory, right? It's like the number of colors, right? The limit that we're really taking here is that we're studying a CFT where most of the CFT degrees of freedom are not charged under this U1 symmetry, which is some statement that the central charge, which the total number of degrees of freedom of the CFT, which is, I hope I convinced you, is proportional to the ADS radius in units in Planck units to some power, is much bigger than this 1 over q squared. So 1 over q squared, remember, is the coupling in front of the Maxwell term. And that measures, say, the spectral density of the gauge of the current. It measures how many of the degrees of freedom carry the charge. Okay, and so basically what we're going to do is solve quantum electrodynamics in n to de Sitter space in some approximation at finite density. Before we do that, so a sort of indication that this was something we could do was a step taken by Subir, which was intended as a holographic model of a Fermi liquid. And the starting point is a picture which is common in a direction commonly known as ADS-QCD, maybe some of you know about it, which is a toy model of the ground state of a confining gauge theory. So far we've been talking about the holographic dual of the gauge theory, which is in a conformal phase, right? So the geometry of ADS goes on forever. There's thinking of it as the RG flow, that's saying that there are modes of arbitrarily low energy. In a confining phase, you expect that there's a mass gap, right? That means that at some point, as you lower the energy, you're going to run out of stuff. That's an indication that a confined geometry should stop. And so a very crude picture of that is just to take ADS with its radial coordinate z and then just stop at some value of z equals z minimum, z maximum, so I'll call it zm, and put a wall there. Okay, so this is a toy model of a confining geometry. And so this picture is a picture of the spectrum of a Dirac fermion in this cutoff ADS geometry. Notice that there's a gap here related to the cutoff. And notice also that there's a finite spacing between these levels, which just comes from, you have to have a 0 of Bessel functions at that place. Okay, and now let's turn on a chemical potential that shifts the bands, and some of them will start to fill, and that filling will back react on the gauge field. And so Subir solved this problem in a Hartree-Fock approximation where you just do this over and over again. So you find the eigenfunctions given the potential, fill the bands that need to be filled, and redo it until it converges. Okay, so the answer is that the system in the bulk is a Fermi liquid. It's just a Fermi liquid in this box, a box which is determined by the dual gauge dynamics by this confining geometry. Okay, and it describes a Fermi liquid coupled to a confined gauge theory. So basically, we've gotten rid of all of the interesting gauge theory degrees of freedom, and so there's just a fermion on both sides of the duality. Okay, so something to notice, and is kind of, I think, the motivation behind that construction, is that if we have a situation with lots of low energy charge degrees of freedom, charged under a gauge field, then this kind of vacuum polarization physics, so here's the gauge field, it produces loops of these charge degrees of freedom. It screens the gauge interactions. The confining state of the gauge theory is, the confinement is enforced by the strong gauge interactions. And so if effects like this weaken the gauge interactions, you might think that you could cause the thing to deconfine by adding more low energy charge degrees of freedom. And the effect of the fermions, so which, one of the things that I want to put in this loop on the gauge dynamics is encoded in their gravitational back reaction. So that, that's just saying that the shape of the geometry describes the result of the gauge dynamics. And so to try to include the effects of the fermions on their back reaction and the gauge dynamics, we need to somehow, we need a slightly better model of the confining geometry. And so a slightly better model, which I won't describe to you, is called the ADS soliton, where there's a good reason that the geometry ends because there's some circle that wants to shrink. And so we made some very naive first attempt at putting some fermions in this geometry and seeing what they did. And so here's a picture of some profiles of the metric functions in this geometry. And this is what happened when we tried to add some fermions. So basically, the geometry got a little longer is the answer. So which is, it's developing more infrared degrees of freedom. But then our numerics broke down. And we realized that in order to address this question, we need to understand what the endpoint of the transition might be. Where can it go if in fact it does deconfine? And so we had to answer this question. Yes, please.
Is this fermion here is the fundamental or joint?
You're asking me about the fermion in the gauge theory.
Yeah.
The fermion I'm talking about is a gauge invariant fermion, right? It's some composite operator made out of whatever this gauge theory stuff is.
So what I'm saying is that if then it is just the order of n to the zeros, right?
What is?
Degree of freedom of fermions.
I'm not sure what that means.
Because you consider one of the Newton constant as n to the square.
Sure.
So I mean, what I'm saying is that how fermion, which is order of n to the zero.
I don't know what that means. I don't know what you mean by the fermion is order of n to the 0.
No. What I'm saying is that what kind of degree of freedom can react to gravitational to n to the square degree?
Well, okay. So I think I understand the kind of question you're asking. So so we're used to the idea that classical fields in the bulk that can have some order 1 gravitational back reaction, right? Like in the holographic superconductor, for example, there's some scalar field that turns on, it changes the infrared geometry, right? And in this Thomas-Fermi limit I described, we had some density of some fluid, which was basically a classical fluid, which its presence changed the infrared geometry, right? It got rid of this equals infinity CFT. So now I'm solving the same problem, but I'm just not making the Thomas-Fermi approximation. So it's just that there's fermionic matter. Certainly, neutron stars exist, right? That is a change in the geometry of space-time caused by some density of fermions. It's the same idea. I'm just trying to understand it better, right? But from the field theory point of view, it's a fair question. You could ask me, who is this fermionic operator that I've been making a big deal about, whose correlation functions I've been computing and looking for Fermi surfaces in? And the answer is, well, that depends on the microscopic realization that produces this gravity dual, but it's some operator which is gauge invariant. It's invariant under any gauge redundancies of the gauge theory. It carries this U1 charge. In examples I know, it's something like the trace of a adjoint fermion times some other adjoint scalars, that kind of thing. But more precisely, I can't say. Yes?
So in your analysis, you are assuming this G Newton to go to 0, right?
That's the approximation which justifies ignoring the gravitational back
So
reaction.
then, after considering that, how is your approximation different from Thomas-Fermi approximation? Can you just
Oh, good. Yeah, I'm sorry. Yes, I want to say this much more precisely. It's the same as what Sabir was doing. It's that we're not treating the fermions as a fluid. We're actually, well, okay, it's not exactly the same as what Sabir is doing. So we're actually filling the Fermi sea. Right? It's the correct thing.
But won't that, in this regime, won't you be able to describe, I mean, you're still working the Thomas-Fermi approximation
No.
where it's valid, right?
No.
That I want to understand. I mean, what is the different thing that you're doing?
So, I don't know, in natural language, it's the difference between Thomas-Fermi and density functional. That helps. This is more like density functional theory, not
Well,
Thomas-Fermi theory.
I would have said it's Hartree-Fock.
Okay.
I mean, I think the thing is you're allowing the chemical potential to vary over the constant wavelength of the fermions.
Yes, that's right.
In Thomas-Fermi, it's got to be a constant over the constant wavelength.
Yes, that's right.
Now it doesn't have to be.
That's totally correct. Yes, that's right. Okay, so this was a messy first attempt but let me explain more precisely what. Let me explain a question that we needed to answer before we can really do that. Sorry, is there another question? Oh, so a zeroth order question that we need to answer is, what could the state of the bulk fermions be if the geometry has a horizon? And so let me answer that question basically by solving the same kind of question that Sabir was solving, but thinking of this ZM, this cutoff on the geometry, really as a cutoff. I want to think of it as an artifact of an infrared cutoff procedure that I'm going to then remove. So I want to ask if I can take the limit that this cutoff goes away to find a state of the fermions just in anti-de Sitter space. So this is what I mean by QED and ADS. So I'm going to fix the geometry to be ADS, no back reaction, but put an infrared cutoff that I'm going to then remove. So the problem we need to solve is, solve the Dirac equation in the background of some fixed electrostatic potential, use that to compute the density of the fermions, use that density to source an electrostatic potential, solve Gauss's law, and plug that back in there. Okay, so a little bit more precisely, we're going to put this hard wall at some z equals zm and then try to take zm to infinity. This is the Dirac equation, right? That's this equation, and this is what I mean by this Gauss's law. There's and this density is you fill the Fermi state, you sum over the levels below the chemical potential of the squares of the wave functions of those levels. So this is explicitly going beyond the Thomas-Fermi approximation, right? These things are not point-like. And remarkably, this limit exists. It's in some ways kind of surprising. This is a picture. So let's look at this picture first. This is a picture of the electrostatic potential as a function of the radial coordinate. This is the density as a function of the radial coordinate, and it's a series of answers, in which we take Zm larger and larger, and it's approaching some kind of limiting profile. And I claim that this double prime is minus that. It actually doesn't look like it, but it is. And so somehow the electrostatic repulsion and Pauli exclusion supports the fermions against falling into the Poincare horizon. There's, ADS is like a gravitational potential well, but they're sort of holding themselves up out of it. And as we increase Zm, these three plots are successively growing Zm. These bands that we saw in anti-de Sitter space with the cutoff, the chemical potential moves some of them below zero, but they, as we take Zm to infinity, you can see a continuum is developing. This continuum is, roughly this is the light cone of the ADS4, and it's filling in inside, and there are some bands outside the light cone. So this thing is a Fermi surface. Sorry, I can say a little. Sorry.
Calculation, you also include the whole light bands.
Yes, that's right. That's right. Yeah. So that's what we're doing differently from you. So we're really filling all the bands and we're normalizing the charge.
So what kind of cutoff on the
Okay, good. So that's the subject of this slide. So for once, you're asking me the question I want you to ask me. So the charge density that we're computing more precisely, so it's a sum over modes that we need to fill, and but notice that each mode is labeled by a momentum in the transverse directions, and so really there are many cutoffs. Okay, so there's a UV cutoff on this ADS radial coordinate, this epsilon that we talked about yesterday. There's a bulk UV cutoff, which is that we're solving the Dirac equation on the lattice. So the radial direction is, has some finite spacing, and so that's also a cutoff here. There's a UV cutoff on this K integral, which is, it's just a hard cutoff there. And then there's this infrared cutoff on the ADS radial coordinate. It's just ridiculous. Okay, so since we're doing quantum electrodynamics in 3+1 dimensions, you might expect that we have to worry about charge renormalization, and you would be right. And okay, and so basically this is a formula for the renormalization of the charge, and it's a simple geometric series because we needn't include loops of the gauge field, and so it's only this bubble diagram that we need to think about. So it's just screening. It's just that the charge is screened with the susceptibility that's computed by this density. Okay, so one check that we're not totally insane is that each K mode of this Dirac equation is a 1+1 dimensional fermion field. And actually, I shouldn't have written that there because it spoils the surprise. But so it has an action that looks like this. The mass is the real mass, and the momentum is the imaginary part of the two-dimensional mass. And if you use the Dirac equation, you can show that the density in each mode should be independent of r when the mass in K goes to 0. This is just a consequence of the Dirac equation. It's inevitable. And so, I thought we could use this as a check on our numerics. And I got very upset when it wasn't satisfied. But then I realized that this object here is actually the divergence of the chiral current for fermions coupled to a vector-like gauge field, which participates in this famous chiral anomaly. And in fact, the numerics got it right. So I was, the numerics are smarter than me. Okay, and so this answer that I described, this ground state. This is at fixed K. This is for each, actually it's for K goes to 0, this statement. Because it's, when K non-zero K is some explicit additional term in the divergence of this current, proportional to some fermion bilinear. Yeah. It would be interesting to use this to learn some physics. I did not, we just used it as a check. Okay, so this answer that we found has the following interpretation along the lines of the semi-holographic business I was saying. The answer is a Fermi surface coupled to a relativistic CFT with a gravity dual. And by the same kind of fermion bilinear coupling. And we can interpret the evolution of the electrostatic potential in C as a statement about how much of the chemical potential, as seen by the degrees of, is left over to be seen by the degrees of freedom of wavelength of order Z after being screened by shorter wavelength modes. The convergence of the equations of motion demands that this goes to 0 in the extreme infrared, that it's necessarily completely screened. And so, and that fact means that the Fermi surface survives this coupling to the CFT, that there's these modes inside the light cone, which describe these CFT degrees of freedom, and the Fermi surface is here. And if I want to couple via a bilinear, a mode that sits here and a mode that sits inside the light cone, I'm going to have a hard time preserving translation invariance. So it's just kinematically forbidden for this CFT to kill this Fermi surface. And so in the pro limit, the quasiparticles survive. That happens because this infrared CFT is associated with the ADS4, the infrared region of the ADS4. But I've just demanded, by taking this weird G Newton goes to 0 limit, that ADS4 is the same as the UV ADS4. The whole geometry is just ADS4 because of this artificial approximation I've taken. Whereas if we include the gravitational back reaction, which it's kind of fun to call it Landau damping, the infrared speed of light can be different. It can, and in particular, this can be inside the light cone, and the story can be more interesting. Yes?
If you start including the gravitational back reaction, would you have some non-zero torsion in the...
Non-zero who?
This is a fermions.
I didn't hear. Non-zero what?
Torsion in the geometry.
Torsion. What's torsion?
I mean, in some sense, the two indices of the crystal symbol won't be commutative.
I don't think that's true. Maybe there's some description where you can use such a thing, but the definition of the I never write Christoffel symbols ever. I don't believe in them.
Generally, if you take fermionic back reactions into account in the geometries, you generally get non-trivial torsion.
I'm not aware of this statement. You can explain this to me later, but yeah, you can. I don't know about that. Okay, so now I want to include the gravitational back reaction. So this is work done by Andrea Elias, who's just finished at MIT and is going to work with Subir, where we're not going to take any limit. And the motivation is what I just said, that when we include the effects of the gravitational back reaction, which is dual to the effects of the fermionic modes on the gauge theory dynamics, the infrared geometry can be different from the ultraviolet ADS, and we can hope that it provides some sort of happy medium between this crazy z equals infinity thing, where we didn't include any back reaction. That's what we get if we don't include the fermions at all, but we include the gauge fields. A happy medium between that and the classical electron star, where there was too much back reaction. Okay, right. So this is too interesting, and this is not interesting enough, and so maybe we'll find something in between when we take the intermediate approximation. That's the hope. Okay, so this hard wall that we've been using as an infrared cutoff is not going to fly when we want to include gravitational back reaction, because it's not covariant, right? You can't just stick a wall somewhere in a theory of gravity, right? You just can't do that. And so instead, as an infrared regulator, we're going to use a regulator that was used by Withers, Rangamani, and Gentle in the context of holographic superconductors, which is we're just going to put the field theory on a sphere. So that's a perfectly good covariant infrared cutoff, right? And we're going to put the field theory on a sphere S2 of radius r. Another virtue of this regulator is that it provides unambiguous infrared boundary conditions. It tells us exactly what to do in the infrared end of the geometry, whereas the wall you have to kind of make something up that preserves unitarity. And so we're gonna make an ansatz for the line element, which is of the following form, where there's this sort of global conformal factor beta, and then there's this alpha function which controls the sizes of these spheres. Okay, so the bound when alpha of z equals 0 is the radius of the sphere that the CFT lives on, and then there's the gauge field. Okay, and so the boundary conditions we're putting on these metric ansatz is that near the UV it looks like ADS, which is the condition that beta goes linearly in z. You can convince yourself that then it's going to look like 1 over z squared near the boundary, which is ADS. And in the infrared, alpha should have a linear 0 at some Zm. That's the sphere smoothly shrinks in the infrared. Okay. You could write the ADS soliton in these coordinates. Well, sorry, no, I'm sorry. The ADS soliton involves an extra circle. The answer is no. The answer is yes, it's different from the ADS soliton. Because the ADS soliton involves an extra circle, right, which shrinks somewhere. Here, it's the spatial sections that the field theory is living on that are shrinking. Okay, so the
But the limit R goes to infinity, it never shrinks, right? You don't want it to shrink.
So here's a picture of the geometry. This is a picture of the geometry at fixed time. Right, so this direction is an S2 that the field theory is living on. So here's z equals 0. And think of, the CFT lives here. And here's z equals Zm. This is alpha equals 0. So it's just the bulk geometry at fixed time is a ball.
No, but you want ultimately to take the limit of Z and goes to infinity.
The thing we really want is to take a limit that R goes to infinity. Yeah, that's right. So alpha of z equals 0 is R. It's the radius of the sphere it's living at. We want to take the limit. Zm is, okay, yeah, so this is a very important question. There is a relationship between Zm and R, which is determined by the dynamics, which we don't know a priori. Right? The system we're going to study has two parameters. It has a chemical potential. It has two-dimensional ingredients. We're going to turn on a chemical potential, and there's a radius of the spatial spheres that the CFT lives on. And those are the only two scales in the problem from the point of view of the CFT, and the physics only depends on their product.
So what I'm trying to get at is that maybe your geometry is too restrictive because you're someone saying that even when the sphere completely R,
Yes.
deep in the IR,
Yes.
it basically looks like a point.
Yes, that's right.
And
Yes.
that may not be the right limit. And maybe that the system is clearly infinite and you've got space that's not.
Your point is well taken. So like before, we're thinking of this Zm as an infrared cutoff, right? And so the hope is that as we turn up the density, actually, we get to pick Zm, right? We're actually Zm that we're choosing, and we're determining R as an output in practice. And so we're hoping that we can take Zm to infinity, and that it'll be just as innocuous as it was in the previous case. That we can identify a limit that the geometry approaches as it goes to infinity, where it does decompactify. So you're right. We want to take Zm to infinity, and we want that to describe the field theory and the thermodynamic limit, where the thing we're interested in is mu r big, right? Because we want to study a lot of stuff on a big space.
You want to take Z to infinity without the geometry approaching a sphere even at infinity.
Well, the hope is that, like in this case, like in this solution that I showed you, there's still a Zm in every one of these pictures, but
the spatial section is still infinite everywhere at all Zm.
that's right.
That's a little better.
You're right. You're right. It would be nice if we didn't have to do this, and I would love to know a way to get around it. Yeah, you're totally right. But the hope is that there would be some infrared region of the geometry that we just don't care about, and that we could identify the limit by thinking about what happens outside that region. Yeah. So I should emphasize this is an ansatz, right? It's an ansatz for the solution, which may not be the best idea, but it was what we were led to by trying to solve the problem. Okay, so I'm going to work in units where mu is 1. The chemical potential has the units, so the thing I'm interested in is varying R. I want R to become big to take the thermodynamic limit. Okay, so again, we solve the problem in 2 steps. So this is the basic code that someday there'll be a basic compiler that will you can type this into and it'll solve the problem. Maybe I think Andrea may have to write it. Okay, so here are a few comments about the technicalities involved in this. So how much time do we have? We have 15 minutes, including questions. Okay, so this motivates a procedure where I don't inflict upon you all of the horrible things that we experienced in solving this problem. But let me just emphasize a few things. So the Dirac Hamiltonian with the ansatz that I wrote down is compact. It's a compact operator in the sense that it has a discrete spectrum. And so that means that some clever adaptation of spectral methods to the boundary conditions at hand, can diagonalize it very efficiently, and produce its eigenvectors, which we need the eigenvectors because those are the wave functions that we're going to fill that produce the density in the stress tensor. And again, we need to renormalize those sources, the charge density and the stress tensor. But the renormalization of the bulk stress tensor is much more complicated than the density, basically because the density only has a logarithmic divergence. That's the familiar charge screening in quantum electrodynamics. In 4 dimensions, there's a log divergence. Whereas this thing has quartic, quadratic, and logarithmic divergences. And most horribly, covariant regulators, any covariant regulator of the short distance divergences, there are many of them, fails to produce some numerical algorithm that we can actually do, which is really horrifying because we have to explicitly break general covariance as a step towards producing a covariant stress tensor. It's really terrifying. And so we had to resort to a point splitting regulator combined with what's called adiabatic subtraction. Raise your hand if you've read the part of Burrell and Davies about this. Okay. All right. And I need to say that any deviation from the path of truth and righteousness in solving this problem is just death. Okay, so this slide is explaining the adiabatic renormalization. I'm going to skip it. It's there's some horrible juggling of different ways in which a quantity can be bad. And there's some cancellation of various badnesses against each other, leaving behind a renormalized stress tensor, which is covariant, conserved. It has the correct Weyl anomaly. What other good things it has to have? Yeah, and it's right. Okay, so yeah, I'm going to skip this. And this is these are the results that we find. So first, we set the Newton constant to 0 and reproduced our previous results with the hard wall. So these pictures are basically the same as the pictures I showed you before. There's an important difference, which is that actually the dots, the lines that are here are actually only represented, the real values are at discrete L because we're studying the thing on a sphere. So they're spherical harmonics and not continuous plane waves. And so really only K goes like L over R, points are allowed, but at large R they happily fill in. And this is the same kind of plot that I showed you before. And then we turned on Newton's constant. For the radius of the sphere less than 3/2 of the ADS radius, the fact that there's a gap in the spectrum in ADS means that when the chemical potential is below that gap. This is in units where mu is 1. And so just nothing happens and the solution is global ADS. And that'll be a dashed line below. The metric looks like this. Really the metric does look like exactly this picture that I've drawn. When we turn up when we make the radius a little bit bigger, the gap in the fermion spectrum goes below the chemical potential, and we find gravitating electron star solutions. So these 3 pictures are the alpha function on top, the beta function here, and the chemical potential as a function of the radial coordinate for successive values of Zm. So I'm varying Zm and trying to make it bigger and bigger like we did before in the G Newton equals 0 case. And okay, so these are lovely gravitating electron star solutions. Let us appreciate their beauty. But then I have to tell you some bad news, which is there's actually never a Fermi surface. None of these pictures has. If you look at the fermion spectrum for each of these cases, there's never a band that comes down and hits the omega equals 0. No, the fermion density is non-zero, but there's no. If you compute the fermion 2-point function, it's there's never a Gappel's modes of non-zero K.
Well, on the finite spatial system anyway, so
That's true.
is that what we mean there? There's never a Fermi surface for a finite system anyway, right? Is that the reason?
No, I don't think so. No, well. So by Fermi surface I mean these kinds of bands that come down, right? The bands that like separate from the continuum. I'm using a bulk perspective on the calculation of the fermion 2-point function, right? And I'm saying that doesn't happen.
Certainly
Yeah.
in this theory, if I remember right, there's a Luttinger theorem, right? That you just take the
Yeah, that's
And
true.
the volume, you get the density.
There's a bulk
What
Luttinger
happens
thing.
to that? No, forget about poles. Even though there's no poles, there's still the volume
Yeah.
of the surface equal to the number of particles.
Yeah, that must be true. Yeah, yeah.
So then how do you have a finite density without having a Fermi surface?
Yeah, we should. There's a good answer to this question, which let's talk about it later. And the reason that I didn't worry about this is because of the following pathology. Because, R is finite is the basic reason. So notice the following horrible thing, really horrifying thing. So I'm trying to increase Zm, thinking of this as an infrared cutoff, and I want Zm as Zm grows. I want it to make the radius of the sphere that the field theory lives on bigger. And so that's happening, right? You see, so alpha of 0 is the radius of the sphere. That's these values here. And as I increase Zm, it happily grows. But then notice, as Zm starts to get bigger, it stops growing. These lines just kind of bunch up here at some fixed value of the radius. And so we're failing to approach the thermodynamic limit. The thing that's happening instead is that beta, the other metric coefficient, this one, is blowing up. It's blowing up at a finite value of Zm. So this is a picture here of this is Zm, this is beta for various values of Q, and it's just blowing up. And so looking at the metric ansatz again, beta blowing up is actually what happens if it means that the Dirac operator is decompactifying. It's like what would happen if there's a horizon, but it's not exactly a horizon in the geometry. And so some personally more bitter news is that in this regime where this crazy thing is happening, the Thomas-Fermi approximation actually works pretty well. And so we could use it to approach what's happening. And the conclusion is that there's really a transition. There's a phase transition in finite volume, which is happening because that's possible because of large n, where the Dirac operator is decompactifying. And the location of the critical value of Zm for various Q is accurately predicted by Thomas-Fermi. So this is the critical value of Zm as a function of Q computed in Thomas-Fermi, and these dots are the correct calculation, which is much more expensive, and so there are only 3 dots. Okay, so a happy statement about this, that's the plus sign means, is that we've found an interesting quantum phase transition, which looks like deconfinement of this system. Deconfinement in the same sense of going from a low density to a high density, driven by turning on the chemical potential. Well, the answer is I didn't tell you what the density was. Yeah. Okay. Driven by the fermion density, and the diagnostic of the transition. It's not the most physical thing from the point of view of the field theory. Well, no, I'm sorry. It's that this bulk Dirac operator is becoming non-compact.
What is beta?
Beta is the metric coefficient, the conformal factor. Well, I don't know the analytic form of it, so that makes it hard to say exactly what the nature.
What is the physical meaning of beta with infinity?
Well, the physical meaning.
Is it just something about the central charge of the dual theory or the IRCFT or something?
Oh, well, that might be interesting. The answer that I have to that question is a very practical one. When this happens, the bulk Dirac operator becomes non-compact. And the compactness of the bulk Dirac operator is like the 0th order step in our construction, right? So it's a phase transition to a regime where we can't calculate.
Non-compact means it has a continuous spectrum.
It has a continuous spectrum, exactly. Okay, so that's the negative thing. It's an obstruction. It's a wall between us, the region where we've been able to study, where the Dirac operator is compact, and the thermodynamic limit, and the limit where this R goes to becomes arbitrarily large. And the accuracy of the Thomas-Fermi approximation in this regime is a mystery to me that maybe I think probably people understand this, but I don't at the moment. Okay, so let me make some comments about this. It may seem like we went through a lot of trouble here, and I guess we did, but it's still a lot more tractable than just trying to simulate a strongly coupled many-body system that has a sign problem. Like, at least we know what to do, even if it's hard. One interesting thing, which when we find a real physical solution, will want to answer this. So I tried to convince you yesterday that the radial dependence of the bulk fields encodes the running of the couplings in the field theory, right? That like the value of the bulk field coupling to some operator O at some radial position R encodes what is the associated coupling in the field theory at that scale. And so it's a little bit interesting to ask, what is the holographic interpretation of the information in the bulk fermion fields, which obviously the fermions aren't couplings. And a possible answer to this is given in a formalism being constructed by Sung-Sik Lee, which is pretty interesting. And so, finally, there's a big open question, at least for me, of how to get beyond this deconfinement transition. So maybe we need to directly study the non-compact Dirac operator. We need some other regulator. Obviously, we have to go beyond this ansatz. And more generally, without biasing the question by the things I've tried so far, I think it's worthwhile to ask what other Fermi surface states can arise holographically. Okay, so that's the end. I have some comments about what I mean by this statement, which I don't know if you. This is, let me say a little bit about this. I think we can agree that holography is great because it gives us some solvable toy models of strongly coupled systems. But as with any toy models, they're only useful if you ask them the right questions. And so questions you shouldn't ask are, for example, you shouldn't use them to compute critical exponents, because those are determined by the masses of the bulk fields, which depends on which string vacuum you're in. So that's why I call it a landscape issue. We saw that thermodynamics doesn't really do a good job of distinguishing weak and strong coupling, right? In the n = 4 Sebring-Mills, the free energy changes by a factor of 3/4 between lambda equals 0 and lambda equals infinity. It's kind of ridiculous. The same thing happens in Lavsky CD. Transport is actually very different, so that's kind of good. People have learned a lot from that. So in perturbation theory, 8/S is some divergent thing, and at strong coupling, it's 1/4 pi. So, some questions that I'm more optimistic about are this one I've talked about today, far from equilibrium physics. And I think a general, reason to be hopeful is that people are, just not that smart. Physics is hard, and so having this kind of pictures is, it's a good idea. All right, that's it.
Talking about, so I worked on the bosonization paper in a magnetic field, but
yes, I forgot to mention that. Sorry.
yeah, we're a bit worried. But you have this. You were saying how you could use the Carroll anomaly to do some physics. But if you're treating the fermions as 1 + 1D anyway, you can just bosonize them. There's a huge number of
Yes.
moieties with different effects of mass that depended on K.
Yes, no, that's right. So this, good. So before your paper came out, I spent some time thinking about whether we could use some kind of bosonization, because we were having this horrible time of figuring out what to do. And I thought about it for a while, and I realized that I can bosonize these fields for a fixed K, and then I thought about what I would have to do to couple them, and the coupling between those bosons is very, very horrible. It's very non-local, except in a large magnetic field.
Yeah.
So the thing I forgot to mention is that these guys found the first gravitating quantum electron star.
Actually, we didn't gravitate it.
Oh, really?
No.
Oh, cheaters.
We couldn't gravitate it because, we could, but you get nothing interesting because you've taken a limit where the magnetic field is huge compared to the energy of the fermions.
Oh, I see.
So nothing can affect the geometry. So we wrote down all the equations and worked out what they are.
Oh,
But nothing will happen.
I see. Okay, I hadn't appreciated that.
What's your name actually?
Mike Blake.
Sorry?
Mike Blake. Mike Blake from yeah. So yours is the first.
I see. Okay, that's somehow a relief.